Okay, this is going to be Chapter 18, Communications, and after completion of this chapter, you'll be able to understand the duality of EMS communications, the history of radio communications from ground to satellite, a breakdown of radio architectures, bandwidths, and technologies, the phases of EMS communications from the initial call for help to turning the care over to hospital staff, and the standardized radio report for communicating with physicians. Communication and teamwork. Teamwork is an outward demonstration of the power of communication. Paramedics play for two teams. They actually play for the public safety team, which goal is public safety through control and command of public emergencies, and the healthcare team, which ranges from primary care providers to rehabilitative services. Communication interfaces occur in both oral and written forms. In the oral form, we give reports all the time. We'll call in and talk to the doctor, may be requesting for orders, or we would give a report on the patient orally whenever we actually transfer the care to the healthcare facility. And in the written form, we should leave a run report, a finished run report of what we actually did or what happened to the patient in our care. History of radio. James Clerk Maxwell hypothesized that an electrical or magnetic disturbance could spread across an invisible substance thought to fill space, like waves on an ocean from a distant storm. This theory was substantially correct. Electrical current passes through wire and creates a field of electromagnetic energy around it as it passes. Alternating current, electricity that flows to and fro through a wire, repetitively creates and increases fields. At smaller frequencies, these fields tend to collapse or dissipate over time. When electricity approaches 10,000 CPS, the electromagnetic field tends to radiate outwards, and the electromagnetic field is sustained. The telegraph, which was a close relationship to the development of the radio, a system of communication that transmitted information over wires, predominant communication method during the 1800s. The first telegraph message was sent by Samuel Morse. Morse code became the prominent means of rapid communication. Guglielmo Marconi utilized the work of Heinrich Hertz. In 1887, Hertz caused a spark to leap across a gap and create an electromagnetic wave, i.e. either waves or Hertzian waves. Marconi invented a spark transmitter, a primitive black box with an antenna that could transmit the spark or signal over a distance to a receiver that would produce an audible snap. That snap, in turn, could be used similarly to the telegraph's Morse code. Wireless communications grew very rapidly. Early radios operated in either low frequency or medium frequency ranges, and they were subject to a great deal of atmospheric interference, and were therefore reduced to the use of Morse code during that time frame. What we're showing you here is figure 18.2, radio waves in the electromagnetic spectrum. And radio waves, if they had a higher frequency, we could actually see them. But the radio waves themselves are just out of our visible light spectrum. An example of this, things that they do to reformulate pictures, would be radio telescopes. Radio technology. First mechanical radio wave generators were restricted to a maximum wave of 100 kilohertz. Electronic generators, or oscillators, markedly expanded properties. The audio signals produced from a microphone was impressed upon a radio signal, and this was called a radio frequency carrier. Through modulation techniques, this message can be carried through antennas, and we know some of those. Amplitude modulation changes wave's height, and frequency modulation changes the wave's speed, and we'll look at two of those here in a second. The length of the antenna is the function of the length of the wave. is the functional length of the wave. The lower the frequency, the longer the radio wave. Quality of many radio transmitters suffered with interferences and all kinds of interference during this time frame. Interference from extraneous electromagnetic energy, heard on the radio as crackles and dead spots, sometimes called static. And then when we talk about static, we have ways of eliminating a little bit of static. We have squelch, which is squelch control, and this reduces the amount of signals received between transmissions, narrowing reception of the radio waves and eliminating background interferences. And then there's such a thing called carrier squelch as well, which eliminates background static during pauses in a transmission, essentially muting the radio between transmissions and thereby improving message quality overall. And then there's coded or tone squelch, and this permits a radio to receive only the intended signal. And these are figure 18.3 AM radio transmissions versus FM radio transmissions. Amplitude modulation is on top, variations, and then frequency modulation, which is speed. Radio frequency. Radio waves are transmitted literally at the speed of light. The differences in the radio waves is the frequency, and this is measured in hertz, or cycles per second. The human ear is able to detect sound in the form of waves in 15 hertz to 20,000 hertz range. Human voice is able to produce a sound in the 200 hertz to 2500 hertz range. The radio spectrum goes from 3 hertz to over 1 trillion hertz. And this is figure 18.4, which we'll look at here in just a second. We also have crystal clear transmission, which is tighter radio waves. They're capable of being transmitted over land as a ground wave, provide remarkable quality as long as there were no obstacles in the line of sight. High-frequency radio antenna could be directed toward the sky and overcome obstacles of the line of sight. Satellite phone systems provide worldwide coverage. Obstacles are high terrain that can block the view of the satellites whenever they're going on the horizon. Low Earth orbit, or LEO, satellite technology, large number of satellites in orbit, constantly crossing the sky and creating a grid of interlocking cells of coverage. Now, this is the radio frequency spectrum, figure 18.4 in your book. And I would look over a few of these. I believe you have a couple of homework questions over this. Very low frequency from this range here. 0.03 to 0.3, low frequency. 0.3 to 3, medium frequency. 3 to 30, high frequency. 30 to 300, very high frequency, or VHF. 300 to 3000, ultra high frequency, or UHF. 3000 to 30,000, super high frequency, or SHF. And then 30,000 to 300,000 is EHF, which is extreme high frequency. Two types, ground and sky. The distance that the ground waves travel is a function of its length. Skywave, tropospheric, radios bounce the radio signal off of the ionosphere in the direction of the receiver antenna. This is wave propagation. Radio systems, system architecture, arrangements of radio components, land mobile architecture, which we will take a look at, a land mobile architecture here in just a second. Land mobile architecture had base stations, mobile radios, simplex radio, which only allows one-way communication, or duplex radio, which allows two-way communication, or multiplex radio. And multiplex permits you to talk and transmit audio signals as well as data simultaneously. Computer-assisted radios. Channel crowding may cause a high-priority EMS radio transmission from a portable radio to be suppressed for a more powerful mobile transmitter from another department. Using computers, multiple users can communicate over fewer frequencies, and this is done through trunking. The computer selects the frequency based on the availability. Cellular system architecture. Cell phones or cellular telephones are low-powered wireless transmitters. Each tower provides a service area, an IESL. Each cellular phone has a forward link to the tower and a reverse link. And this is figure 18.8, and we'll look at that one too. Cellular telephone, portable cellular telephones are convenient, but they lack the range. Transportable cellular telephones are more powerful, but with the big battery, they're less convenient. A satellite mobile telephone is dependable and secure connectivity. And alternate communication devices they would talk about here in this section would be a fax machine or facsimile machine, mobile data terminal, or a personal digital assistant. And this is the model for land mobile radio architecture. There are several channels. The radio antenna is pretty high, 40 to 100 foot. You have a fixed frequency, high power transceiver in the dispatch area. And then in the car, up to 25 watts of antenna here, or when you're broadcasting, would pick up to 25 watts on the antenna, and a fixed frequency radio transceiver here. So these would communicate back and forth to one another. Generally speaking, the signal would go out the antenna, hit this antenna, and be transcribed to the device or the radio. And this is components of a cellular system. So forward link and a reverse link is the example of this, and these are actually in cells. So as the car is traveling, the reverse link would be to the tower before. And the forward link would be to the tower ahead. And you would go essentially from one cell service to the next. Mobile equipment control that would bring it back so that the mobile operator could actually communicate with the units. And then some sort of network interface equipment that would be able to put this out, not only record, do all the things that dispatch does, record the information, put out dispatch information, locate the actual individual. Now, some of this information is behind. Currently, there is technology to triangulate your position using cell phones as well. Public Safety Communication Act of 1934. The President of the United States has control over all governmental radios. The Federal Communication Commission has control over civilian use of radios. Early EMS radio communications. The white paper, Accidental Death and Disability, that kind of started our profession, spoke for the need for dedicated frequencies for EMS and advocated for a centralized radio and telephone communication center. And we have it today. It's called 911. Called for the creation of a single nationwide telephone number for all emergency services. Phases of EMS communication. Detection. First thing we're going to talk about here. President's Commission on Law Enforcement and Administration of Justice recommended a single universal emergency number, and this was 911, who had specially trained call takers for public safety access points to take down information regarding the nature of the emergency to pass along to fellow workers and responders. E911 includes a callback feature and a location identifier except for cell phones. Now, we do have ways of geocoding current locations on cell phones. Pre-arrival instructions. Chief Brunassi ordered that all callers receive instructions on how to self-rescue before responders got there, and this was medical self-help. So these were the basis of our current dispatch cards that are utilized today. Notification and response. Greatest danger is posed for the paramedic from secondary motor collisions. You step out, you got to be careful, you get hit by another oncoming traffic. Medical priority dispatching. Sent the right response to the right person at the right time. First due report is a brief synopsis of the scene size-up obtained by the first arriving EMS responder. We don't use TIN codes anymore because TIN codes are confusing. Many actually prefer that this be done in plain English. Radio conduct. Frequently, paramedics use standard nomenclature, affirmative, negative, and standby, as well as concise radio reporting style to ensure that clear messages get through. And this is figure 1812, Communication Center or Public Safety Access Point. Phases of EMS communications continued. Treatment and transport communications. The paramedic shares a special relationship with the emergency physician that requires a more complete disclosure of the patient's condition than would be expected from an EMT, and that would include things like history of present illness, past medical history, things that you found on the physical examination, their vital signs, focused physical examination on specific areas, what your field diagnosis is, discussion of the treatments provided up to that point in time. The echo technique is used in this a lot. The physician gives an order and the paramedic repeats it back to him exactly as received. And then we generally give an alert report as we're coming in to notify the receiving facility. Radio difficulties in this. The public safety wireless network study indicated that 15% had problems with static, batteries, or both. 23% complained of signal fading. 32% complained of channel crowding. The Fire and EMS Communications interoperability study indicated that less than 35% of the agencies indicated confidence in interoperability of their radios during a large-scale task force operation. So we probably still need to do a better job of that. Conclusion on this. Whether communicating with other members of the healthcare team or public safety team, quality of communications is important to overall teamwork. Working as a team and optimizing communications at both levels will help facilitate patient care and the patient's recovery from a medical emergency. References for this section can be found in Richard Beebe, Professional Paramedic, Volume 1, Foundations of Paramedic Care, First Edition, pages 320 through 336 of Del Mar Learning. And if you have any questions concerning this chapter, feel free to give me a call. My name is Roy Smith, smith@imsa.net, or 405-219-7613. Thank you.